Welcome to my new calculus channel. My name is John Gabriel. Today I'm going to talk to you about the general definition of area and volume, but I'm going to focus mainly on areas. So let's begin. Since the time of the ancient Greeks, concepts such as area and volume have not been that well understood. And until I came along, no one had a clue that area and volume can be defined in a general way. That is, one formula for all areas and one formula for all volumes. So, area is well defined as the product of two arithmetic means. Arithmetic mean of all the vertical line lengths and the arithmetic mean of all the horizontal line lengths. And it's demonstrated to you over here in these pictures. So if you had to take the arithmetic mean of all the horizontal line lengths in this rectangle, it would always be equal to this side here, wouldn't it? And how do we know that? Well, the arithmetic mean is given by k times w divided by k, which is always w. Similarly, the height will always be h. Okay, so this is something that no one before me actually realized. And it is in fact the reason why calculus works. The mean value theorem does exactly what I'm showing you over here. And I was the first to realize this. So I was also the first to prove the mean value theorem constructively, using both your bogus calculus and the new calculus. So area really is just equal to w times h, but both w and h are arithmetic means. And you might say, well, how does this apply to all areas? Well, I'll show you. It should be relatively easy first to see how this is true in the case of all other planar geometric objects. For example, a parallelogram, triangle, trapezium, rhombus, etc. So for example, a triangle is always half the area of a parallelogram with the same base. And we know that parallelograms on the same base between two parallel lines always have the same area, and hence we've essentially proved that all triangles are half the area of a parallelogram on the same base, and hence half the product of the arithmetic means. Okay? And you can verify in your own time that this is true for any planar geometric object. So what about irregular area? What about this area here, which is quite irregular? This particular one is really a triangle, and I show you that you can also find it using a definite integral. Well, for example, 3 times 3 is 9, which is the area of this whole square, and half of it is 4.5. Similarly here, this is done using integral calculus, but really, you're looking at two arithmetic means here. You're looking at an average or an arithmetic mean of all the vertical lines, compared with the arithmetic mean of all the horizontal lines, which is all the lines that are horizontal in this area here. So the product of those two gives you the definite integral. Okay? As you can see, a definite integral is simply the product of two arithmetic means. So this is true for any line or path integral. And in case you didn't know, all integrals are line or path integrals. And I'm not going to show that to you in this video because it would take too long. But what you're looking at here is the fundamental theorem of calculus, and it wouldn't be possible without the mean value theorem. This here is what you typically see set equal to f prime c. In other words, this is the arithmetic mean of all the vertical line lengths in this region, or whatever the region is. Okay? And when you multiply it by the interval length, which is the arithmetic mean of all the horizontal line lengths, all the ones that are horizontal, then you get the area. Okay? So this times this gives you the area, and that's why the definite integral is a product of two arithmetic means, this arithmetic mean and this one, okay? Your orangutan teachers didn't know this unless they learned it from me. Now, you cannot mix arithmetic means of areas above and below the x-axis because the arithmetic mean of ordinates below the x-axis is negative. So you wouldn't obtain a true mean. You either need to have them all negative or all positive, and that is why you evaluate areas separately and then add them up. So if f prime of x is an acceleration curve, like you see inside here, then you can disregard the above rule, where you interpret the physical value of the integral as the change in velocity. And here's the change in velocity, right? Okay? So it's not strictly speaking a change in velocity. And the orangutans who wrote this article here, that's what they said. It's the net change. It says the net change in velocity is the integral of acceleration. That's false. The net change would mean this whole expression here divided by b minus a. That is the change. Okay. One velocity subtracted the other one is not a change. So whichever moral lecturer compiled this here doesn't know what he's talking about. And this here, by the way, is not the net change theorem. It's the fundamental theorem of calculus, which is derived in one step from the mean value theorem. And there are many theorems masquerading as something else. For example, the average value theorem, it's also derived from the mean value theorem. The fundamental theorem for integrals and all those other theorems are derived directly from the mean value theorem. And I was also the first to realize that, but your orangutan lecturers still haven't come to terms with those facts. And it would probably take a long time until they learn how to do calculus properly. So there is no such thing as a net change theorem. As you can see now, a definite integral is simply the product of two arithmetic means. Can you guess how the volume is defined generally? Well, I'm sure that if you're astute enough, you would have guessed that the volume is defined generally as the product of three arithmetic means. This is a new calculus channel, and I'm John Gabriel. Till next time, goodbye.